March 14, 1944, Recklin Airfield, Germany. The captured P-47 Thunderbolt, serial number 42-22490, sat under armed guard, painted in hasty German markings. Luftwaffe test pilot Hans-Werner Lerche walked slowly around the massive American fighter, his engineer's mind cataloguing every detail. He'd flown over 120 different aircraft types during the war, including captured British Spitfires and American P-38 Lightnings. But something about this particular Thunderbolt troubled him in ways the technical briefings hadn't prepared him for. Small rectangular panels were visible beneath each wing, just forward of the main flaps. They looked almost insignificant, barely noticeable against the aircraft's overall bulk. The German engineers had examined these mechanisms during their disassembly inspection, documenting them with characteristic thoroughness. They understood the basic principle. Dive recovery flaps, surfaces that deployed electrically to help pilots recover from the extreme high-speed dives that made the P-47 so devastating in combat. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. What they couldn't understand, what kept the engineering staff at Recklin awake reviewing calculations, was how these delicate-looking mechanisms could possibly survive the forces involved. The American pilots were reportedly diving their Thunderbolts past 550 miles per hour, pulling out with forces exceeding 7 times gravity. The stresses should shatter those flaps like glass. The mathematics were clear. At 7.5 times gravity, a 14,000-pound fighter generated over 105,000 pounds of force. The wing loading alone exceeded anything German structural engineers would dare attempt. The dive recovery flaps, extending into the airstream at transonic velocities, faced pressures that should rip them from their mountings instantly. German wind tunnel data predicted catastrophic failure. Combat reports from Luftwaffe pilots told a different story. Lerche had read the debriefing statements. American P-47 pilots were diving on German formations from 30,000 feet, accelerating to speeds where the controls became rigid with compressibility effects, then deploying those supposedly fragile flaps and pulling out of dives so steep they seemed suicidal. They were recovering at altitudes that gave them time to climb back for repeated attacks, and the flaps weren't failing, they weren't breaking. The Thunderbolts kept coming back. The disconnect between what should happen and what was happening represented something deeper than just superior American engineering. It revealed a fundamental difference in design philosophy that German engineers were only beginning to comprehend as they examined captured equipment in detail. 6 months earlier, on September 9, 1943, Lieutenant Robert Samuel Johnson had discovered exactly what those dive recovery flaps could do when used by a pilot who understood both their capabilities and limitations. He'd been escorting B-17 bombers over northern France when German fighters intercepted the formation. Multiple Focke-Wulf FW-192s climbed aggressively toward the bomber stream. Johnson and his wingman held altitude advantage at 28,000 feet. They rolled, inverted, and dove. The massive Pratt & Whitney R2800 engine roared as Johnson pushed the throttle to war emergency power. The indicated airspeed climbed rapidly past 400 miles per hour. At 25,000 feet, he was indicating 460 miles per hour. The acceleration continued. Johnson had practiced these dives dozens of times during training. He knew the sensations, the increasing force pushing him back into the seat, the steadily building pressure on the control stick as airspeed increased, the way the aircraft's response to control inputs became sluggish, then rigid, as localized airflow over the wings approached the speed of sound. At 520 miles per hour indicated, compressibility effects became severe. The elevators lost most of their authority. The stick felt like it was set in concrete. Johnson's P-47D was diving nearly vertically, accelerating continuously as it plunged toward the German fighters below. This was the moment that separated trained pilots from dead ones. Johnson reached for the dive recovery flap switch. Electric motors whined as the rectangular panels beneath each wing rotated downward, extending into the 520 mile per hour airstream. The immediate effect was dramatic. The dive recovery flaps changed the airflow pattern over the lower wing surface, disrupting the shock wave formation that was causing the elevator to lose effectiveness. Simultaneously, the flaps generated substantial drag, slowing the Thunderbolt's acceleration through the compressibility region. Most importantly, the flaps produced a powerful pitch-up moment. Even with the elevators largely ineffective due to compressibility, the aircraft's nose began rising. The recovery wasn't instant. Johnson pulled firmly on the control stick with both hands, maintaining steady back pressure as the P-47 descended through 20,000 feet. The forces were building rapidly. At 15,000 feet, the Thunderbolt entered denser air. Compressibility effects diminished as true airspeed decreased relative to indicated airspeed. The elevators gradually regained effectiveness. The pullout began in earnest at 12,000 feet. Johnson's body compressed into the seat as gravity forces exceeded 6 times normal. Blood drained from his brain toward his lower body. Vision narrowed to a tunnel. He grunted forcefully, tensing leg and abdominal muscles to raise blood pressure and maintain consciousness. The acceleration peaked at approximately 7 times gravity. The P-47D's wings flexed visibly under the enormous load. Structural members throughout the airframe groaned under stress. The dive recovery flaps extended fully into a 500-mile-per-hour airstream, while the aircraft simultaneously pulled 7G forces, absorbed pressures exceeding anything German engineers would consider survivable for such mechanisms. The flaps held. No rivets popped. No actuator arms bent. No mounting brackets cracked. At 8,000 feet, Johnson completed the recovery and immediately pushed the throttle forward. The kinetic energy from the dive converted to altitude as the Thunderbolt zoomed upward. Within 45 seconds, he regained 26,000 feet without the engine working particularly hard. The entire attack sequence from initial roll-in to altitude recovery consumed approximately 70 seconds. Johnson had fired a 3-second burst into an FW-190 during the dive, observing hits before the German fighter rolled away trailing smoke. He was back in position to provide mutual support to his flight within 90 seconds of beginning the attack. When Johnson landed at Halesworth, ground crews examined his aircraft routinely. The dive recovery flaps showed no damage, no looseness in their mounting, no indication they'd just survived forces that would have destroyed similar mechanisms on any German fighter. The maintenance sergeant signed off the aircraft as fully mission-capable. It flew 2 more combat sorties that same week. At Recklin, German engineers struggled to understand how this was possible. They had examined similar flaps in exhaustive detail after capturing Lieutenant William Roach's P-47D on November 7, 1943, when Roach mistakenly landed at the German-held Carpic Airfield in France. The captured Thunderbolt, nicknamed Beetle, had been transported to Recklin and subjected to the most comprehensive evaluation the Luftwaffe technical services could conduct. The dive recovery flaps on Beetle consisted of electrically actuated panels, approximately 36 inches long and 12 inches wide, mounted beneath each wing just forward of the main flaps at roughly 20 to 25% of the mean aerodynamic chord. Each flap was hinged along its forward edge. When activated, electric motors rotated the flaps downward to an angle of approximately 55 to 60 degrees. German metallurgists examined the flap construction microscopically. The panels themselves were fabricated from heat-treated aluminum alloy, with thickness varying from 0.04 inches at the trailing edge to 0.1 inches at the hinge line. The hinge mechanism consisted of precision-machined steel brackets with hardened steel pins. The actuator arms used high-strength steel with surface treatments to resist fatigue. The quality was exceptional. But exceptional quality alone couldn't explain survival under the documented combat conditions. The calculations were straightforward and unforgiving. At 550 miles per hour indicated airspeed, the dynamic pressure acting on a fully deployed dive recovery flap exceeded 240 pounds per square foot. With a flap area of approximately 3 square feet per side, each flap faced over 720 pounds of aerodynamic force trying to rip it from its mountings. Simultaneously, during a 7.5G pullout, The wing structure itself was flexing and twisting under loads that multiplied every component's stress. The combination of high-speed aerodynamic pressure plus severe G-loading plus wing flex should produce catastrophic failure. German engineers conducted their own wind tunnel testing using scale models of the P-47's dive recovery flaps. At the National Advisory Committee for Aeronautics, Ames Aeronautical Laboratory, American engineers simultaneously conducted similar tests, though obviously with different objectives. The NACA report, designated ACR 5D19 and dated May 1, 1945, documented tests on a 0.3 scale model of the P-47D equipped with several dive recovery flap configurations. The wind tunnel tests measured drag coefficient and pitching moment coefficient at various Mach numbers up to 0.8 Mach. The data revealed why the flaps worked and why they survived. The dive recovery flaps didn't simply extend flat into the airstream like barn doors. Their carefully calculated angle and positioning created a complex aerodynamic interaction with the wing's lower surface. The flaps generated a powerful upwash that energized the boundary layer flow over the aft wing section, helping maintain elevator effectiveness even in the compressibility regime. Simultaneously, the flaps disrupted shock wave formation over the wing's lower surface. This delay in shock wave development meant the aircraft's aerodynamic center moved aft more gradually, reducing the severity of the pitch-down moment that characterized compressibility tuck. The drag generated by the flaps was substantial but not overwhelming, approximately 15 to 20% increase over clean configuration at high speeds. This provided enough deceleration to prevent continued acceleration into deeper compressibility, while still allowing the pilot to maintain control authority for recovery. The structural survival came from sophisticated design details that weren't immediately visible during inspection. The flap mounting brackets distributed loads across multiple wing ribs rather than concentrating stress at single attachment points. The actuator mechanism included deliberate flexibility, allowing the flaps to deflect slightly under extreme loads rather than transmitting full force to the mounting structure. The hinge design permitted small amounts of rotation beyond the nominal deployment angle, functioning as a mechanical fuse that absorbed peak loads. German engineers recognized these features during inspection. What they couldn't replicate was the material quality and manufacturing precision required to make the concept work reliably in combat conditions. The aluminum alloys used in American aircraft construction consistently exceeded German specifications for strength, ductility, and fatigue resistance. Strategic materials like chromium, molybdenum, and vanadium, increasingly scarce in Germany by 1943, remained abundant in American production. The surface treatments applied to critical components, including the dive recovery flap hinges and actuators, used processes that required specialized equipment and controlled atmospheres. The hardening and tempering procedures produced material properties that German industry could achieve in laboratory conditions but couldn't maintain across mass production. Most importantly, the quality control applied throughout American aircraft manufacturing meant every component met design specifications. There were no substitute materials forced by shortages, no relaxed tolerances to speed production, no skilled workers replaced by inadequately trained forced labor. The dive recovery flaps that survived 7.5G pullouts at 550 miles per hour did so because they were manufactured exactly as engineers intended, using materials that met all specifications, assembled by workers who understood their job, inspected thoroughly before installation. This level of manufacturing fidelity had become increasingly difficult for German industry to maintain. Lieutenant Colonel Heinz Baer, who commanded the 2nd Gruppe of Jagdgeschwader 1 from April through May 1944 before being shot down and wounded, later provided insight into German pilots' perspective on P-47 diving tactics. In post-war interviews, Baer explained that experienced Luftwaffe pilots learned through bitter experience to avoid certain engagement scenarios. If American Thunderbolts held altitude advantage above 25,000 feet, engaging them was extraordinarily dangerous. The P-47 pilots would dive from superior position at speeds German fighters couldn't match. The dive attacks came too fast to evade effectively. Then, before German fighters could respond or defensive measures could coordinate, the Thunderbolts would recover using those mysterious dive recovery flaps and climb back to altitude where the turbo supercharger gave them insurmountable performance advantage. Baer noted that the psychological impact on German pilots was severe. Knowing your opponent could dive on you at speeds you couldn't match, attack with devastating firepower, then escape before you could counterattack created a constant sense of vulnerability. Some German squadrons began refusing to climb to high altitude altogether, concentrating their efforts on attacking bombers during climb or descent when P-47 escort was less effective. This defensive posture reduced German fighter effectiveness dramatically. Attacking bombers from below exposed German aircraft to defensive fire from the bombers' belly turrets. It gave German pilots less time to aim carefully before P-47 seconds could dive to intervene. It conceded air superiority across large portions of German airspace. The dive recovery flaps, seemingly minor features when compared to engine power or armament, had helped transform tactical doctrines and strategic outcomes. On February 8, 1944, during a massive escort mission to Frankfurt, the 56th Fighter Group encountered approximately 60 German fighters attempting to intercept the bomber stream. The engagement demonstrated dive recovery flaps under maximum combat stress. Captain Walker Bud Mahurin led a flight of 4 P-47Ds positioned at 30,000 feet, 5,000 feet above the bomber formation. German fighters were climbing from multiple airfields. Oberst Hannes Trautloff's unit, elements of Jagdgeschwader 53, coordinated with other formations to mass nearly 60 Bf 109 seconds and FW 190 seconds against the bomber stream. The German attack plan called for simultaneous strikes from multiple angles to overwhelm the American escorts. Mahurin rolled inverted and called the attack. 4 P-47Ds dove nearly vertically. The indicated airspeed increased rapidly. At 28,000 feet, 400 miles per hour. At 25,000 feet, 460 miles per hour. At 23,000 feet, 500 miles per hour. Compressibility effects became pronounced. Mahurin activated his dive recovery flaps at 515 miles per hour indicated. The flaps extended into the airstream. The forces acting on those mechanisms at that moment exceeded anything German wind tunnel predictions suggested was survivable. Over 700 pounds of aerodynamic force per flap, multiplied by acceleration forces approaching 6G as Mahurin began the pullout. The flaps held, the nose pitched upward. Mahurin fired a 2-second burst into a Bf 109 that had been climbing confidently toward the bombers. 8 Browning 50 caliber machine guns delivered approximately 200 rounds in that brief engagement. The German fighter disintegrated under the concentration of heavy machine gun fire. Its pilot, Feldwebel Ernst Schröder, a 16 Victory ace, was killed instantly. Mahurin completed the recovery at 18,000 feet, having descended 12,000 feet in approximately 35 seconds. He immediately zoomed back toward altitude, the accumulated kinetic energy from the dive carrying him upward with minimal engine power required. 45 seconds after firing, Mahurin was back at 28,000 feet, repositioned to support other squadron members. His dive recovery flaps retracted flush with the wing's lower surface, showing no damage, no vibration, no indication they'd just survived forces that exceeded German engineering predictions for catastrophic failure. The engagement continued for 18 minutes, across 70 miles of German airspace. P-47 pilots executed repeated diving attacks using the same tactical pattern. Dive from altitude at maximum speed, deploy dive recovery flaps during compressibility regime, fire concentrated bursts, complete recovery, zoom climb back to altitude. The 56th Fighter Group claimed 16 German fighters destroyed that day. German records documented 14 aircraft lost with 9 pilots killed. More significantly for the strategic picture, bomber losses during the period when P-47 escort was present remained far below expected. 5 B-17 seconds were shot down during covered portions of the mission, compared to devastating losses during unescorted segments. The dive recovery flaps had enabled protective tactics that saved hundreds of bomber crew lives over the course of the campaign. At Recklin, Hans-Werner Lerche finally flew the captured P-47D designated T9 plus FK, formerly William Roach's Beetle. His test flight followed weeks of ground examination and cautious systems familiarization. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Lerche climbed to 25,000 feet and began exploring the aircraft's high-speed characteristics. At that altitude, the P-47's turbo supercharger provided full-rated power, while German fighters were already losing performance significantly. Lerche rolled into a steep dive. The indicated airspeed increased rapidly. At 480 miles per hour, he deployed the dive recovery flaps. The effect was immediate and dramatic. The nose pitched upward noticeably despite the dive angle. The rate of acceleration decreased. Most importantly, Lerche retained control authority that would have been completely lost in any German fighter at those speeds. He pulled back firmly on the control stick. The P-47 responded, beginning the recovery, even though compressibility effects were evident throughout the airframe. The pullout generated approximately 5 G-forces, less than the 7.5G maximum American pilots reportedly achieved in combat, but sufficient for Lerche to understand the system's effectiveness. He leveled off at 15,000 feet and immediately zoomed upward, gaining 3,000 feet of altitude in less than 30 seconds using accumulated energy from the dive. Lerche's technical report acknowledged the dive recovery flap's effectiveness in clear, professional terms. The system allowed recovery from dives at speeds and angles that would be uncontrollable in German fighters. The American pilots' standard tactic of attacking from altitude, diving at extreme speed, and recovering quickly for repeated attacks was not just aggressive flying, it was a sustainable tactical doctrine enabled by specific engineering solutions that German industry couldn't replicate. The materials weren't available. The manufacturing precision wasn't maintainable at production scale. The quality control couldn't be assured with forced labor replacing skilled workers. German engineers understood what needed to be done. They lacked the resources to do it. The final irony appeared in post-war analysis conducted by both American and German aviation specialists. The dive recovery flaps represented only one small element of the P-47's overall design, but that element, properly engineered and manufactured to exacting standards, enabled tactics that amplified every other advantage the aircraft possessed. High-altitude performance from the turbo supercharger mattered only because pilots could safely dive from high altitude to attack and then recover to regain that altitude advantage. Rugged construction that survived battle damage mattered only because pilots could press attacks aggressively, knowing they could escape through diving if necessary. Heavy firepower from 850 caliber machine guns mattered only because pilots could position for optimal firing solutions through diving attacks. The dive recovery flaps, those unremarkable rectangular panels extending into 500 mile-per-hour airstreams, while subjected to 7.5 times gravity, tied the entire tactical system together. They survived because American industry could manufacture them correctly using proper materials. They worked because American engineers understood both the aerodynamic principles and the structural requirements. They enabled victory because American doctrine used them as part of a comprehensive tactical system. German Oberst Werner Mölders, before his death in November 1941, had pioneered many of the tactical innovations that made the Luftwaffe so formidable in the early war years. His Finger 4 formation, the Schwarm, provided mutual support while maintaining tactical flexibility. His emphasis on altitude advantage and disciplined execution created a tactical framework that German fighter pilots followed throughout the war. But Mölders had developed his tactics fighting opponents in Messerschmitt Bf 109 seconds and Focke-Wulf FW 190 seconds against Hurricanes, Spitfires, and early American fighters. He never encountered an opponent that could dive away at speeds his aircraft couldn't match, recover from those dives using technology his engineers couldn't replicate, then return to altitude advantage before he could reposition for counterattack. The tactical innovations Mulders created assumed rough parity in aircraft performance, with victory determined by pilot skill, tactical positioning, and aggressive execution. The P-47 with dive recovery flaps broke those assumptions. It introduced a capability gap that couldn't be closed through better tactics or braver pilots. By mid-1944, Luftwaffe training programs were producing pilots with increasingly limited flight hours. Fuel shortages meant new pilots arrived at operational units with perhaps 50 hours in type, compared to the 150 to 200 hours American pilots received. These inexperienced German pilots faced veterans flying aircraft that could exploit every tactical mistake mercilessly. A novice German pilot might fail to maintain proper altitude awareness. American P-47 pilots at 30,000 feet would spot that mistake immediately. The dive would come at speeds the German pilot had never experienced even in training. The American pilot would deploy dive recovery flaps, complete the attack, and recover before the German understood what happened. The experienced German pilots who survived into 1944 understood the threat clearly. They developed counter-tactics within the constraints of their equipment. Some tried to bait American fighters down to medium altitudes, where German fighters maintained performance advantages. But disciplined P-47 pilots refused to follow, maintaining altitude advantage and declining engagements on unfavorable terms. Others attempted to intercept bombers quickly from lower altitudes, attacking fast and escaping before P-47 escorts could dive on them. This gave German pilots less time for careful aim and exposed them to concentrated defensive fire from bomber formations. Neither approach solved the fundamental problem. American fighters controlled high-altitude airspace, and German fighters couldn't contest that control without accepting catastrophic loss rates. The engineering team at Focke-Wulf attempted to design dive recovery mechanisms for the FW-190 inches, late 1943. The project consumed significant engineering resources at a time when German industry was already stretched beyond capacity. Initial designs proved too heavy, adding weight that degraded already marginal climb performance. Simplified versions lacked the structural strength to survive the forces involved. The materials required for a functional system, particularly high-strength steel alloys for actuator mechanisms and precision bearings, were increasingly unavailable for aircraft production. Those materials were being diverted to U-boat construction, tank production, and other higher priority programs. Even if the design problems could be solved, manufacturing a reliable system at production scale was impossible given Germany's deteriorating industrial situation. Republic Aviation in Farmingdale, New York, and Evansville, Indiana, meanwhile, produced P-47 Thunderbolts at rates exceeding 300 aircraft per month during peak production. Every single aircraft included dive recovery flaps as standard equipment, manufactured to consistent specifications, installed by trained workers, inspected thoroughly before delivery. The cumulative effect of this production capacity delivered thousands of P-47 seconds, equipped with dive recovery flaps, to operational units throughout 1944. Each aircraft enabled tactics that multiplied American numerical advantage. Each dive attack executed with proper technique achieved disproportionate results. The Germans faced not just superior individual aircraft but an entire system, industrial and tactical, that they couldn't counter. Major Robert Samuel Johnson completed his combat tour in May 1944 with 27 confirmed victories achieved in 91 missions. Every single victory came flying P-47 Thunderbolts. His success rate, approximately 1 victory per 3.4 missions, exceeded what most air forces considered achievable over sustained combat periods. Johnson attributed his survival and success directly to proper use of diving tactics enabled by the P-47's unique capabilities, including dive recovery flaps. In his memoir Thunderbolt, co-written with Martin Kadin, Johnson emphasized that individual pilot skill mattered less than properly executed tactical doctrine based on aircraft capabilities. A mediocre pilot following correct doctrine would defeat an excellent pilot using incorrect tactics. The dive recovery flaps were integral to that correct doctrine. They allowed aggressive attacks at speeds that rendered German defensive responses ineffective. They permitted rapid recovery that maintained American altitude advantage. They enabled multiple attack cycles within single engagements, multiplying each sortie's effectiveness. Johnson described the physical sensations of combat dives repeatedly throughout his memoir. The increasing pressure as airspeed built, the gradual loss of control authority as compressibility effects intensified, the moment of deploying dive recovery flaps and feeling the nose pitch upward, the crushing G-forces during pullout that compressed his body into the seat and narrowed vision to a tunnel, the exhilaration of zooming back to altitude with energy to spare for repeated attacks. These weren't unique experiences limited to ace pilots. Every P-47 pilot trained in these techniques. Every squadron practiced the tactics until execution became instinctive. The dive recovery flaps made the entire tactical system reliable enough for average pilots to execute successfully in combat. That democratization of effective tactics, making victory accessible to competent rather than exceptional pilots, represented perhaps the flaps' most significant contribution. Lieutenant Colonel Francis Gabreski, who became the highest-scoring American ace in the European theater with 28 confirmed victories, flew his final combat mission on July 5, 1944. 15 days later, while strafing Bassenheim Airfield at low altitude, his P-47 struck the ground, damaging the propeller and forcing him to crash land in German-held territory. He spent the war's final 9 months as a prisoner. In post-war interviews spanning decades, Gabreski consistently credited Colonel Hubert Zemke's tactical doctrine and the P-47's specific capabilities for the 56th Fighter Group's success. When they arrived in England in January 1943, most pilots believed the P-47 was too heavy and cumbersome for effective combat. British pilots told them they'd be slaughtered. Then Zemke showed them a different approach. Stop trying to turn with German fighters. Start using real advantages. Altitude performance, diving speed, structural strength, and those dive recovery flaps that let you survive the extreme forces involved in high-speed attack and recovery. The same aircraft that seemed like a liability became the foundation for air superiority over Germany. The strategic impact of dive recovery flaps, tiny rectangular panels that most people never noticed, rippled through the entire air campaign over Europe. The 8th Air Force's strategic bombing offensive depended absolutely on achieving air superiority that allowed bombers to reach targets and return with acceptable losses. P-47 escort fighters, using diving tactics enabled by dive recovery flaps, achieved that air superiority. They destroyed German fighters at rates that German training programs couldn't replace. They forced German fighters to avoid engagement or accept devastating losses. They created conditions where American bombers could systematically destroy German oil production, aircraft factories, transportation networks, and industrial capacity. The bombing campaign succeeded not because individual bombs were particularly accurate or devastating, but because the cumulative effect of thousands of sorties destroyed Germany's ability to wage modern industrial warfare. Every successful bomber mission depended on fighter escorts that controlled the airspace. Those escorts controlled airspace through tactics that exploited diving attacks. Those diving attacks worked reliably because dive recovery flaps allowed pilots to survive forces that would otherwise be fatal. The chain of causation ran directly from small engineering details to strategic outcomes. German intelligence services understood this chain completely. Their technical reports documented American capabilities accurately. Their tactical recommendations to frontline units were sensible and professional, but understanding what needed to be done provided no path to actually doing it. The dive recovery flaps required materials Germany couldn't obtain, manufacturing precision Germany couldn't maintain, quality control Germany couldn't assure, and production capacity Germany couldn't match. Knowledge without resources was strategically useless. By August 1944, Allied forces had landed in Normandy and were advancing across France. The Luftwaffe's fighter force had been ground down through attrition that combined combat losses with fuel shortages and pilot training limitations. German fighters still appeared over the battlefield, but in smaller numbers and with noticeably less aggressive tactics. P-47 Thunderbolts transitioned increasingly to ground attack missions, carrying bombs and rockets to support advancing armies. The dive recovery flaps that had enabled air superiority now helped pilots survive ground attack missions against intense anti-aircraft fire. They could dive steeply on targets, release weapons accurately, then pull out sharply and escape before German gunners could track them effectively. The tactical versatility demonstrated one final advantage of American engineering philosophy: design robust systems with performance margins that enable multiple mission types. The dive recovery flaps weren't optimized exclusively for air-to-air combat. They worked equally well for ground attack, fighter-bomber operations, and any other mission requiring steep dives and rapid recovery. German fighters, designed with tighter performance margins and less engineering conservatism, lacked that versatility. The Bf-109 was an excellent air superiority fighter, but a mediocre ground attack platform. The FW-190 served adequately in multiple roles, but excelled in none. The P-47, with its dive recovery flaps, could execute any mission profile successfully. Hans-Werner Lerche survived the war and provided extensive debriefings to Allied intelligence services. His memoirs, published in German in 1977 and translated to English in 1980, included detailed technical assessments of captured Allied aircraft. His evaluation of the P-47's dive recovery flaps was characteristically professional and objective. The system worked exactly as designed. It enabled tactics that German fighters couldn't counter. The engineering was sophisticated but not revolutionary, just American designers solving known problems with adequate resources and proper materials. The real advantage wasn't the flaps themselves, but the industrial system that could design them, manufacture them to specification, install them reliably, and deliver thousands of aircraft so equipped. That industrial system, Lerche concluded, represented a level of capability Germany never possessed, even at the war's beginning, and certainly couldn't match by 1944. The dive recovery flaps symbolized everything about American material superiority. Not wonder weapons or secret technology, just competent engineering applied systematically with unlimited resources. The story of P-47 dive recovery flaps ultimately teaches lessons about industrial warfare that transcend specific technologies or tactical innovations. Material abundance systematically applied through adequate engineering defeats technical excellence constrained by resource scarcity. The capacity to manufacture good equipment in overwhelming quantities outweighs the ability to design perfect equipment in limited numbers. The dive recovery flaps weren't perfect. They added weight, complexity, and maintenance requirements. But they were good enough to enable effective tactics, reliable enough to work consistently in combat, and available in quantities that equipped entire fighter groups. That combination of adequate capability with systematic availability decided the war's outcome more surely than any amount of German engineering cleverness or tactical innovation. The mathematics were inexorable. American industry produced 15,683 P-47 Thunderbolts between 1941 and 1945. Each aircraft from the D-25 variant onward included dive recovery flaps. German industry produced approximately 40,000 aircraft total across all types during that same period, but never solved the dive recovery problem despite understanding its importance. Quality multiplied by quantity equals capability. America possessed both. Germany possessed neither in sufficient measure. The outcome was determined by industrial capacity, applied through competent engineering to create tactical advantages that brave pilots and innovative tactics couldn't overcome. The dive recovery flaps, surviving 7.5G pullouts at 550 miles per hour, proved that truth repeatedly over European skies. Those unremarkable rectangular panels, barely visible beneath a Thunderbolt's wings, represented everything Germany feared and couldn't match. American industrial might translate it into practical solutions, manufactured without compromise, delivered in overwhelming numbers. The technology wasn't revolutionary, the application was decisive. That was how you won air superiority. That was how you protected bombers. That was how you achieved victory through material abundance and systematic excellence. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.